Hello everyone, welcome to OneClass. My name is Shanjida. I'm currently a second year human biology student at U of T. And so today I'll be going over some commonly asked chemistry questions, both at the high school / university and college levels. And so if anyone has any that needs any schoolwork help or needs tutoring, you can check the description box below. And other than that, let's get started. Okay, so our first question here says, what intramolecular forces are present in NH3, which is ammonia? Right, so let's first write NH3, and so this is ammonia. Okay, so basically first let's address the how many intramolecular forces are there, and basically what are intramolecular forces. So your intramolecular forces are forces that hold the bonds between the molecules together in solid or liquid. Okay, and so we can say here that our intramolecular forces are forces that hold the bond together between atoms, between basically two atoms, right? And so basically, so these forces, right, are generally much weaker than intramolecular forces. So these are basically, so basically intermolecular forces are the ones that are weaker. So we can say these are weaker than intramolecular forces. Okay, and so we can say the strength of the intramolecular forces is directly proportional to the polarity of the bonds. So for example, as the bonds become more polarized, the charges on the atoms become greater, which leads to a greater intramolecular force. Okay, so you can relate this to polarity, and so you can say as bonds get more polarized, charges on the atom get greater, so therefore you have greater intramolecular forces. Greater intermolecular forces. So the types of there are four major classes of basically interactions between the molecules. So your intermolecular forces, four types. Of interactions. Okay, and so you have, so number one is the strongest, which is ionic forces. So your ionic forces are formed between your a metal and a non-metal. Right? Non-metal. Okay, so it is between the charged atoms or molecules called ions. So these are between metal and non-metal ions. So these are the highly polarized or charged ionic molecules make the ionic bonds, and so your ionic bonds is among the strongest among all the intramolecular forces. So this is the strongest force. And so the next one you have is hydrogen bonding. Okay, and so your hydrogen bondings, these occur in molecules containing highly electronegative elements like your fluorine, nitrogen, and oxygen. So highly electronegative. Right, so this is fluorine, nitrogen, oxygen. And so these are directly bonded to hydrogen, which are to hydrogen. This is why it's called hydrogen bonding. And so although the bonds possess covalent characters, the difference between the electronegativities of the atoms in hydrogen's bond makes the molecule partially positive and partially negative on opposite sides. So when you're dealing with electronegativity, right, so you would have one atom partially positive and the other partially negative. So the way you can determine if it's negative or positive, you just look at your electronegativity table, and the one that's more electronegative would get the partially negative charge, and compared to the one that's going to be partially positive. So the higher the electronegative number you have, that's the one that's going to have the negative charge on it. And so the next one we have here is dipole interactions. And so these are your other elements besides hydrogen. So these are elements except hydrogen that form bonds with another element with different electronegativity. So you have different elements with different electronegativity. Okay, and so the electronegativity, and this is what creates the dipole-dipole forces. So the electronegativity difference also creates partial charges on different sides of the molecules. Okay, and so what you can say here is that so your difference between the electronegativity between the atoms create so they create partial charges also, right? So the key difference between dipole-dipole and hydrogen bonding would be that your dipole-dipole interactions are formed between other elements besides hydrogen. But the common thing between them is that you have electronegativity in this case, and you have partial charges. So you have to take account the partial charges, where the more electronegative an atom is, that's the one that will have the partial negative charge. And so our last one would be London dispersion forces. Okay, and so this is among the three. So among the four forces, intermolecular forces, this is the weakest force. Okay, so this is the weakest intermolecular force, but however, to increase the strength, the force strength, you have to basically increase the total number of electrons. Or we can say that increase, so we can actually rewrite this as if you want an increase in strength, right, of this force, increases in strength if so this increases in strength, and your electrons, so the total number of electrons also increases. I would also want to add that if you have a lot of let's say your London dispersion, if you have a lot of your London dispersion forces, this will ultimately lead to a strong force, right? Compared to if you only have one. If you have a lot of them, you will have you would generally have a really strong force. Okay, and now in this problem, it is asked to determine what are the intermolecular forces present in ammonia, which is NH3. And so if we go back, so if you have NH3, right, you can see that we have hydrogens, right, present in ammonia. And so we can basically state that it has hydrogen bonding, right? It has hydrogen bonding because the hydrogen bonds. So hydrogen bonds are formed between nitrogen, oxygen, and fluorine. And so in this case, we do have hydrogen bonds, and this is also due to the difference between their electronegativities, which makes the molecule polar. So you can say big difference in electronegativity makes NH3 polar. Okay, so we have an electronegativity chart over here, and so you can basically see that you can basically see hydrogen over here is 2.1 and nitrogen in this case is 3, so that's a big difference. And so this is why the bond is polar. Okay, and so basically as you saw that your nitrogen is more electronegative, this would have your partial negative charge, right? And you write partial like that. So your nitrogen will have the partial negative and hydrogen will have partial positive. Okay. So basically this is what creates your hydrogen bond. And so however, it also has another force, your London dispersion forces. So and you would be thinking why. It's because your dispersion forces are in all compounds basically. So these forces are present in almost all compounds. Okay, so you can also say that you have London dispersion forces in ammonia. And yeah, so these are the two different interactions or forces in ammonia, which is NH3. Okay, and we can see here that they have also mentioned we have hydrogen bonds and dispersion forces, which is correct. Okay, so our next question here says, what is the pH of for a 0.35 molarity aqueous solution of sodium formate if the Ka of formic acid is 1.8 times 10 to the power negative 4? Okay, so a pH, right? Let's first address what does pH mean. And so your pH is basically is a scale. Is a scale in chemistry. To measure how acidic / basic an aqueous solution is. Okay, and consequently the strength of acids and bases are so the pH of acids and bases are related to their pKa, Ka, pKb, and Kb, right? So your pKa, so we can say your pKa, Ka, these are for your acids. Your pKb and your Kb, these are your bases. These are for your bases. Okay, and so this is your Ka is your acid ionization constant, and your Kb is your base ionization constant. And so here we're given that the Ka for formic acid, so we can say Ka is equal to 1.8 times 10 to the power negative 4, right? And if you recall, if you recall that your Ka expression is expressed as, so you have your protons, right, your H, so the concentration of your hydrogen ions, and basically the compound, the dissociated ions from the compound, and your reactant, right, which is the acid. And basically where your hydrogen ions concentration and your anion concentration is it's from the dissociated, it's completely dissociated into the solution, right? And so if you want to relate this to Kb, which we need to find, so what they're saying is to find sodium formate, and sodium formate, so I'll just write here, sodium formate is a base. Okay, and so your Kb, right, so we can write that your Kb is basically the concentration of your OH ions times the concentration of your cation from the base, and your reactants going your denominator, right? So this is basically the ratio. And so basically we can also relate Ka and Kb with the ion constant, basically for water, which is Kw. And so Kw can be represented as Ka times Kb, right? Where your K, this is basically equal to 0.0 times 10 to the power negative 14. Okay, and so this is all these things that are given, and which we need to find the Kb, so the base ionization constant, and from that we can find our pH. And so we can basically write so we need to first write out the balanced chemical equation, right? To find out what is dissociated, what ions are dissociated, basically. And so we can say that the reaction, so these reactions are reacting with water, and it's under equilibrium. So reaction of sodium formate with water. Okay, and we can say here that Na, so your sodium formate, plus H2O, so your equilibrium arrows, and so this is HCHO2 plus NaOH, right? So these are so NaOH is basically the base it makes, and so we can basically rewrite this expression for your Kb as your products, right? HCHO2 over your reactant. So we don't include water here, right? We're just including the aqueous solutions, and so you have NaCHO2, right? But remember your Kb, when you're writing out your expression, you can't really have metals like so it has to be like your actual bases, the ions that are completely dissociated. And so we can rewrite this as HO2, and so this becomes your OH negative, and then this becomes CHO2 negative. Okay, this is your Kb expression. And so we can basically express, so we can basically find the base ionization constant from our previous equation, that Kw is equal to Ka times Kb. And if I just go back, right, our Kw is 1.0 times 10 to the power negative 14, and we're given our Ka, which is 1.8 times 10 to the power negative 4. So we can basically rearrange the equation. So I'll just rewrite Kw is equal to Ka times Kb. So we can find our Kb by isolating Kb by moving Ka over to the other side. And so we basically have Kw over Ka, right? And we just plug in the values, 1.0 times 10 to the power negative 14 over 1.8 times 10 to the power negative 4. And you can put this in your calculator, and you would basically get so I've got 5.555 5.556 times 10 to the power negative 11. So this is your Kb for your base, basically. And so we can basically say that 5.556 times 10 to the power negative 11 is equal to HCHO2 to OH negative over your CHO2 negative, right? And so if you remember that we have to construct an ice table where your ice is basically your initial value change and equilibrium table for the reaction to determine the concentration, right? So because we need your concentration to find your pH, and so we can say, if I rewrite the equation here again, so I'll just rewrite NaCHO2 plus water, and you have plus NaOH, right? And so I'll just construct a table here. So we have the concentration ice table, and we have N, so your reactants, which is NaCHO2. Your products would be your products over here would be HCO, CHO2 and OH, right? And so your initial concentration of sodium formate is given in the equation, which is 0.35. And so we can say our initial value for this, use a different color, for this is 0.35, right? And you don't have your initial concentration for your reactant, so this is going to just be 0. And your reactance is always negative, right? Since we're completely dissociating sodium formate to have your ions, and so you have negative x plus x. And so you can rewrite the equation as 0.35 minus x. This is just x and x. And then what we can do here is rewrite the KB equation and say KB is equal to your reactance, which is in this case now x times x over 0.35 minus x. Okay, and so we can now say that your x squared over, so this is x squared over 0.35 minus x, and your KB, which was 5.5, so it was basically 5.6 times 10 to the power negative 11. Okay, and now we can say, so now we can basically solve for x, right? We can basically say, so you can just basically solve for x, and so you can do the math here, and so when you solve the value for x, this will also give you, this will, so your x, solve x, and you can get we'll get concentration of your OH, right? And so if you do that, you would basically get your OH, you would get here x, right, which is also x. I'll just say OH is equal to basically 4.4 times 10 to the power negative 6. This is what I have got here. Okay, and so now finally your pH can be calculated, or your POH in this case, because we're dealing with bases. So we can say here that POH is equal to your negative log of the concentration of OH. So we can say this is a negative log of 4.4 times 10 to the power negative 6. And so what I get here, so I basically get 5.3 5.3556 as my POH, right? But you see here that the question wants pH, and so to find pH we can say that, so if you recall our equation, we have another equation where your pH plus your POH is equal to 14. So 14 is basically the end point of the pH scale, and this is the further basic it can get. And so we can basically say pH, right? To find pH we can say this is 14 minus POH, and you have 14 minus your pOH is 5.3556, and so I get here 8.644 as my pH. And so your closing statement, you can say therefore the pH of sodium formate, which is also NaCHO2, is 8.644, right? And this indicates it's basic, since your pH scale above 7 is anything above 7 is basic, anything below 7 is acidic, and so this indicates that your pH is 8.644, right? And this is what they have got, and so, right, your solution is correct. Question says, what is hydronitric acid? Okay, so basically your hydronitric acid, we can say hydronitric acid, right? This has, so from the formula you can probably guess that it has hydrogen and nitrogen in it. And so the formula for this would be HN3, right? Not NH3, that would be ammonia, but it is HN3, and this is basically aqueous, you can say. Okay, and so you can, this is also considered a weak acid. So this is a weak acid, and it is soluble in water, right? So because it has hydrogen, so it is very soluble in water, and you can also say it has hydrogen bonds, right? Hydrogen bonding are bonds involved. And yes, it is formed from azide salts, so formed from salts. Okay, and yes, so this is correct. So, okay, so our next question says, how do you calculate the average atomic mass of magnesium given the following percent abundances and isotopic masses? Okay, so as you probably guys know that atoms consist of many forms basically, so those are called your isotopes, where so we can say isotopes are formed by basically a difference in the number of neutrons, right? Because your protons cannot change. It's because your protons and your electrons are always the same in any atom, and so it's basically, therefore it's the change in neutrons which makes different forms of the same element, basically, which are called isotopes. And so here we're talking about magnesium. And so to calculate the average atomic mass, they've given us the abundances and the masses of the other isotopes. And so to do this, the results are, so to calculate the average atomic mass, we have to multiply the percent abundance with the isotopic mass. And so to do this, we can basically take our first given compound here, which is magnesium, the natural occurring magnesium, which has an atomic mass of 24. And so we can say that, so the percent abundance, right, percentage is always out of 100. And so we can say here that, so we can multiply, so we'll just say multiply percent abundance with atomic mass. To get average atomic mass. Okay, so we can say here that, so let's take our first one in this case, which is 78.99%. So let's first express this as a decimal. We can say here is our first case 0.87899, and you multiply this with your atomic mass here, which is 23.98504, right? And so when you multiply these two numbers out, you get So I get 18.9457831 ANU, right? This is basically the units for atomic mass, or U. And so our second one, right, which is magnesium, that has an atomic mass of 25, and this consists of 10%, and so we can express 10% first as a decimal, right? So you basically divide your percentage by 100 to get your decimal, and so we have 0.100 times 24.98584. And so when you multiply these two numbers, you get 2.498584. This is a point, and this is an AMU. And so our third one, which magnesium can be found as, which is magnesium with the atomic mass of 20. And so this consists of 11%, so we put 0.1101 times basically 25.998259. And so when you multiply these two numbers, you get 2.86068315 ANU. Okay, and so now to calculate the total, the average, we can basically add all this together. Okay, so now calculate average. So we're just gonna add all these numbers together. So we have 18.947.831 plus 2.49884 plus 2.8 is 2.860683159. So when you add all this together, you basically get So I basically get 24.305 AMU. Okay? So this is your natural occurring magnesium atom atomic mass. So if we look at a periodic table right here, okay, so you can probably see from group 2 over here that your magnesium is from group 2 and it has a atomic mass of 24.31, so which is basically the same thing that we have got here. And so yes, so this is next question. How do you determine pH from molarity? Okay, so basically just went over this, how pH is a measure of how acidic or basic a substance is. And yes, the range goes from 0 to 14, 14 being the most basic, 0 being the most acidic, and 7 is being neutral. And so molarity is the same thing as molar concentration, is equal, basically not equal, we can say is the molar concentration expressed as, so it's expressed as, so we can say molarity is equal to the number of moles, or so we can say moles, right? And this moles of solute over the volume in liters, basically we can say, or I'm just gonna say liters of solution. Okay, and so basically concentration or the molarity can be used to determine pH. And so if we have, so for example, so I'll just say concentration, or we can say molarity, right? To determine this, we can say can be used to determine pH by so we can say, for example, if I have, for example, we have, let's say we have nitric acid. For example, we have nitric acid, right? H, just HNO3. And let's say this has a concentration of, let's say, 3 concentration is equal to 0.0032 molars, okay? And so since HNO3 with nitric acid is a very strong acid, it will completely dissociate into your protons and your nitrate ions. And so the molarity basically becomes the concentration of, so basically we can say since HNO3 is a strong acid, it will completely dissociate into H plus ions and your NO3 ions. Okay, and so basically the molarity of, so we can say basically molarity of HNO3 is equal to the concentration of your H plus, right? Since when we're talking about pH, we actually take the concentration of your proton in this case, which makes the acid, right? And so therefore you can say pH is equal to negative log the concentration of your protons, right? So we can say since the concentration of your initial nitric acid is 0.0032 molars, we can also say that the concentration of your proton, your hydrogen ion here, is 0.0032. Okay, and so if you compute this, you basically get negative log of 0.02, and so I get pH is equal to 2.49, right? And so basically this is how you can determine pH from molarity, and you just need to know the concentration of your acid or basically base. And so you put that you basically, if it's a strong acid or a base, it will completely dissociate into their individual ions. And so upon that, you can substitute it into your pH equation and find pH of that substance or acid or base. Okay, so we have here molarity. And so this is the example they have given, and so yeah, so this is correct. Okay. Okay, so our next question says, give the IUPAC name for each of the following carboxylic acids. And so we can see that so we're given 4 carboxylic acids here, and we basically have to give the common name or the IUPAC name for basically these acids. And so to do this, let's first address A, okay, or let's first address how our carboxylic acids are derived. So basically your carboxylic acids, you can say carboxylic acids are derived from open chain alkanes. alkanes, right? Your hydrocarbons. And so basically, when you have carboxylic acids, the terminal, so your terminal name, so when you're like, when you have alkanes, the terminal E would be replaced with oic acid, right? And so E basically is, right, if you have like hexane or pentane or anything, so your E, or no, it's the terminal E. So you have your terminal E gets replaced with oic acid, right? That's how you get your carboxylic acid, oic acid, basically, okay? And so basically when your compounds have, so the compounds that have a CO2 or 2H, and so the carbon that has would be, so we can say carbon that has this group basically would be numbered C1. B numbered would be C1. Okay, your carbon 1. And okay, so we can see here that so for A, right, it's given, so we have, so let's draw out A. We have 1, okay, so we have 2 hydroxyl groups, right, and so we basically have 2 carboxylic groups basically, right, here. And so we can basically say any of them can be carbon 1, right, since they're attached to CO2H, right, other of them. And so if you want to count the carbon chains here, we have 1, 2, 3, right, these are the branches. And so if you recall, 3 is prop, and so to name this we have, it's gonna be, and since we have 2, it's gonna be dioic, right? And so we have propan dioic acid. Okay, so this is your propandioic acid. And so B, which consists, okay, so we can write this BHO, C double bonded with an O, CH2, CH, oops, okay, I think I don't have space, so I'll just write this as HO, so we have here 1, 2, 3, 4, 5 carbons. Okay, so I'm just gonna write this like this: 1, 2, 3, 4, 5. Okay, this is your OH, this is your carboxylic, and then you have a methyl group here, and I have carboxylic. Okay, and so to name this, right, we can see that either of them basically can be, so each end could be your carbon 1, and so basically we have two CO2H groups here, and so it's going to be di, right? You have 2, and so we can see if we say this is 1, 2, 3, 3, 4, and this is a 5th carbon, it's going to be pent. And you can see that one of the substituents here is methyl, so we can basically name this as 3-methyl pentadioic acid. Okay, this is your carbon chain. And now, so number C. C is, so we have a hexane. We have a hexane here, and so we have carboxylic group. We have a chlorine substituent, the double bonds, right? And so basically this would be, and so this would basically, so basically this would be your first carbon chain, your first carbon, and so we can say that this is our 2nd, 3rd, 4th, 5th, 6th, and to name this, we can say, so this is gonna be, so since it's this is a benzene ring basically, so the parent chain would be a benzoic acid, and so to name point out the substituents, this is on the 2nd carbon, so we can say 2-chlorobenzoic acid, right? And now, lastly, we have pentene ring, 5-carbon ring. We have carboxylic group. We have okay. And so again, this is our first carbon, 2nd, 3rd, 4th, 5th, and so our parent chain would be pentene. And since our substituent here is chlorine, so, and since this is cyclo, right, this is a cyclopentane, we would basically write this as 2-chlorocyclopentane, and we would actually name the substituent here would be pentanoic acid. Basically. Okay. And so let's see if they've got, okay. Yes. So we have got the first 3 correct. I would actually say D is 2-chloro. Okay. And so this is correct. And so that was the end of our session. If you like this Q&A, please subscribe to OneClass, like, share, and comment on this video, and you can check out our other videos. And if anyone has any personal questions, you can go check out the links in the description box and ask your questions. Other than that, I'm Shanjida, and I'll see you soon. Bye bye.